Good day to everyone. My name is Balázs Mosug, and I'm going to be presenting our results so far towards a JavaScript vulnerability prediction model. As an introduction, I would like to explain why we would need such a thing and why it's extremely useful and great news for any advancements over this topic. So in our current environment, we're trying to create the most complex, the most capable software systems possible. And as such, these codes can be extremely complicated and extremely long. Debugging this and finding issues in them is already a challenge in even of itself. However, finding them before our users would is becoming more and more of an impossibility, basically. To solve this issue, researchers for years have been trying and working really hard to create these automatic software analysis tools that would assist us in finding these vulnerabilities as fast as humanly possible. In recent years, machine learning-based approaches started to pop up in order to further our advancements towards finding a means to predict possible vulnerabilities in code bases. However, these solutions usually come short in some regards, especially when it comes to their explainability, first of all, because they are usually black boxes. It's really hard to know why a certain model would predict something. Like, they don't tell us, for example, if this file is vulnerable for sure, but then why would it be? If a line is like 3,000 lines long, especially in JavaScript, that happens quite often, it is really difficult to find the exact vulnerability that we are looking for. The other thing is that they are extremely coarse-grained, like especially at file, but even function level can be insufficient, especially at low accuracy, because if we have a 70 or 60% chance of a correct prediction, it would be really nice to be able to tell quickly whether the prediction is correct. And the first step towards that is being able to locate the exact reason and line and source for the prediction. This is really difficult to do on file or class level, since these can be extremely large. Both of these issues we've tried to tackle in our own ways. First of all, we work at the line level, which is a lot more fine-grained, meaning that it is as close to be basically instantaneously decidable from the developer side as possible, because they can just see what the exact problem is of the model, why it says that something is wrong. And tying into that, we also provide an explanation of sorts as to why the model thinks that a line would be vulnerable. Of course, this is not a very verbose explanation, that, as we will see in a short while. However, it is still at least something. In some instances, especially, it can be outstandingly helpful to know what the model thinks of a line, how it at least views it, what it sees on it, and why it might think that it is vulnerable. It is also useful when it comes to false positive and addressing them, because we can see that, well, this line is excessively simple, for example, like just a simple variable declaration or something. In those cases, it's likely that it's just a misfire and we don't have to really think about it. Whereas if a file level model would misfire, for example, because it sees an irregular variable explanation, it would be really hard to know that, well, it just misfired because it saw a weird variable name, instead of knowing that, well, it clearly did just that. It is also lightweighted, very extendable in multiple levels. We will cover that in a second. However, it is good to know that it doesn't actually need a very strong hardware to finish what it does, especially when it only needs to look through a singular file. That can be done even on extremely weak computers. And that is really useful, because when it comes to integrating a tool, it is important that the developer's hardware can actually manage using it. And it is very extendable, meaning that one can really easily fit it with their own project, make it more of their own. Here we can see a quick flowchart of how we approached the topic, how we created the tool, and how we come to our first vulnerability prediction. First of all, we created a data set both from GitHub data and already existing JavaScript datasets. This has been then manually filtered to create a vulnerability repository, which we will call from now on a VLR. This is stored in a laxed version. We will soon talk about what that means. And also we create a Word2Vec model. That model has to be trained only once, and it is already trained. If one would get this tool, for example, it would most likely come with the model already pre-trained, so they would basically need to do no training when the tool gets to their machine. Once the VLR and Word2Vec is set up, we only need the system under test, also referred to as SUT from now on. And from these components, we can already start predicting things. The predictor itself uses very basic algorithms, nothing too complicated to calculate the likelihood of a line being vulnerable. It also applies some custom rules that can be added and tinkered with, as we will also see later. First of all, I would like to talk a little bit more about what the VLR actually is and how it comes to be. Of course, it's really important to know this because since the model basically solely relies on this source of information, it is really important for this to be accurate. We have used multiple sources to create this. The main source, of course, has been a data set specifically created for artificial intelligence use. However, we have also spiced this up a little with another CV source. So there are multiple kinds and variations of vulnerabilities in it. This has then been manually filtered, meaning that we have tried to minimize false positive rate as much as possible. Two of our researchers, in fact, did this manual filtering separately. So we have tried our best to minimize these chances. However, of course, human error is still a thing, but we do not believe this to be relevant at this point. These vulnerable lines are stored in a tokenized form. This is done in order for the tokenizer to be not overwhelmed while working. And we could also technically store the Word2Vec results themselves, like the vectors that are created from these lines. However, that would be insufficient when it comes to the modularity of the model, because as it stands right now, it's really easy to swap off a Word2Vec model for another one or add a new rule, and that would kind of break that if we store the lines in the repository in a way that where they are already processed to that point, because then it would be difficult to change some models around. I've mentioned lexing a whole lot already, so let's talk about how we do that. We have used an already kind of pre-existing tool called GSTokens. It's a pretty bare bones solution, meaning that it doesn't have too many tokens by default. However, we added some of what we thought were basics, like JavaScript language keywords such as if, for, while, etc. These are, of course, needed in order to at least register the language as something that's worth looking at. We also added some special string literals such as SQL strings or HTML strings are recognized as their own tokens, meaning that at least these are handled separately. Also, when it comes to numbers, we treat -1, +1, and 0 in a special way, where they are not lagged as a numeric literal, but while every other number is. This is also in order for some specificity when it comes to the examined code. And now, of course, the most important thing of all, how a prediction is actually made for a singular line. This whole process is done for every single line in a system that is currently being tested. First of all, the basic operation is done. The cosine distance between every single line in the vulnerability repository is calculated. Their cosine distance is calculated between the currently examined line, and the smallest of these is selected. Then, of course, it is converted into a likelihood by basically subtracting it from 1. This makes it so that the lower the distance is, the higher the possibility of it being a vulnerability. We then calculate the complexity of the line. This is basically how many unique tokens there are in there. This is actually the main novelty of this approach, because this improves every single result, so every single angle of the results substantially, this makes it so that it flags considerably less lines, which is basically the biggest issue, because of course, if we flagged every line, we would find every vulnerability. However, this reduces the flagged lines so considerably while keeping more of the vulnerability predictions intact. This was really one of the biggest findings that we made. This is of course, first of all, an integer, and it is calculated into being between 0 and 1. It is a pretty basic method, nothing too fancy about it. Once these two metrics are calculated, we just take their average as and that's going to be the line's likelihood of being vulnerable. Then of course we take a threshold, and if it's above set threshold, then we accept it as being vulnerable and flag it as such. This threshold has been tested out to be 93%. We did this by starting at 75% and gradually by 1% each time, increasing up until 100%, and looked at where most of the vulnerabilities are being found, while meanwhile the minimum number of lines are being flagged. This has been done over a development set, of course, not the entire data set. This is only 10% of this has been done over only 10% of the available lines. And 90% of the remaining data set has been used in a tenfold cross-validation in order to confirm that our results are correct. The results of this tenfold cross-validation can be seen in this table down here. To explain what on the far left of the table, we can see the names of the results. They require a little bit of an explanation, so I will. The first is the average results when not applying our rule, and of course when the C is present, that means that we applied our rule. That's why ENR and ECR, that's how they differ. And we can already see that the effect of the complexity rule in action, there are a lot less lines, like a quarter of the lines that have been flagged without applying it. Meanwhile, we lose some of the vulnerable lines that are flagged, but that's way less than what it is, in our opinion, very much worth losing 20% of the vulnerable lines as when it to only flag a quarter of the amount of lines. Below these, we can see the worst and best case scenarios that have happened throughout the 10 folds. In the worst fold, both of them have produced a relatively low amount of vulnerability flags. It is important to note that here the complexity rule has actually a higher flag percentage than what we see in the average, but we still consider this the worst result because it flags a relatively large amount of the code, which basically means that even though it has found a lot of the vulnerable lines, it is not very useful, because looking through 2000 lines is still a lot of work just to find. I mean, 17 vulnerabilities are a lot, of course, but it's still a lot of work to get to them. In the case when we do not apply the rule, everything is just straight worse. There is not even a decent comparison to make. It finds less vulnerabilities by flagging 3 times as many lines. So we can clearly see that in the worst case scenario, the complexity rule holds up. In the best case scenario, it's even more visible. Both of them find every single vulnerable line that is present. However, with the rule in action, it only flags a fifth of the available lines, which basically means that it is a major improvement. It's also worth to note here that while we were working on a fold, we have removed because of course we have worked from our own data set, and in these cases when we did these examinations, we removed the lines of the current suit from the VLR, meaning that if we were looking at, for example, a node file, just as an example, we removed every single node vulnerability from the VLR to minimize the chance that the same project being examined has an impact here. This is a sample of how of what kind of vulnerabilities the tool can find. These are two real vulnerabilities that have been already fixed. I mean, every single vulnerability has been fixed, but these especially point towards our tool being useful. And under them, we can see what the proofing system would do, what proof it would give a developer for, and how that would look like. Of course, here it is just a bunch of identifier name and a couple of punctuation marks. So I mean, one could say that this is not very useful. In this case, of course, it's not, because it's a very complicated and long line. This is what the complexity rule very prefers. But for example, if there was a really long for cycle where it said for identifier name in identifier name where identifier name, we could very easily deduct that, well, this is most likely a misfire, a false positive, because it's just a for cycle. Or if it wasn't that the case, we could at least very easily look at and say that, well, of course, the for is not going to be the problem. So I mean, we can more easily isolate the issues at hand. The second case, there are even less punctuation marks, but still the same thing holds up. The point here is not really to actually tell you exactly how you should fix your issue or how you should come to the conclusion that something is wrong, but it's at least a nudge towards you knowing that what you are looking at is most likely an actual vulnerability, because that's especially because we still flag a decent portion of lines. It is very important for any user to be able to determine whether what they are looking at is how likely it is to be actually a correct result. As a summary and a conclusion, our method is, we believe, is more than capable of producing useful results, and our new rule has brought considerable improvements. Of course, we have not only tried this rule, we have tried many others, such as, for example, looking at the surrounding lines and saying that, well, if a block is vulnerable, that means that a line in said block is more likely to be vulnerable. This rule hasn't helped much. Our hypothesis towards why that would be because these vulnerabilities, as we have seen from the example, are usually located in a single line, meaning that they are not really detectable in blocks. We can see that the method flags about 13% of all lines in average, finding 60% of the vulnerabilities. This, we believe, sounds at least decent on paper. However, especially when it comes to being in usage, this is still crying out for some improvements, since even if it's just 30% of all lines, that could still be thousands of lines. And since this is most definitely not every single vulnerability, it would still require a tester to look at other lines that were not flagged. This could, as in its current state, it is just a priority setting tool. If you want to look through your file, it could point you towards the right direction where you have a higher likelihood of finding lines. However, this can be improved in a number of ways. First of all, of course, creating more sophisticated rules that would take more matters into account, not just the current line's complexity, and also improving the aggregation methods, both taking the average and the way that the complexity rule is normalized back between 0 and 1 are relatively arbitrary, meaning that there is a lot of testing to be done here. And of course, extending the VLR could probably also increase both the likelihood of finding new vulnerable lines and allow us to use more strict rules to further increase performance. That's pretty much it. Thank you for the attention, and I await your questions.
Very interesting indeed. I have basically the one big question. Is this VLR database available somewhere in open access?
The VLR database in itself is not available. However, every single database that we've used to create it is available, and we plan to make both the tool and the VLR used public once we deem the project to be finished.
So it will be eventually available in an open source form somehow. So other researchers can also be, okay, that's great. And the second question, did I understand correctly that when you say line, you basically mean statement, not just a single line in the text, but some statement, which may take a few lines, or am I wrong?
No, when I say line, I mean a line of a text. It's not divided up to statement. These statements, it is a text line.
So if there's a statement which takes 2 lines, for example, A equals to 5 plus 5, and then I say 5 plus, and the 5 goes to the next line, the second 5, then it's going to be 2 lines, right? And you will treat them
Yes.
individually, like separately.
Yes, exactly.
Interesting. Okay. Let me check. Maybe we have questions there in the chat. And how long, that's just a question of the researcher, from researcher to researcher, how long did it take for this project? Like how much time did you spend on it?
Well, if we also count the creation of the VLR, it took over a year. If we only count the development of the tool itself, it's about half a year. So we started around, around August.
So basically creating the data set and then making the tool is just approximately equal amount of effort.
I mean, yes, one could say that, yes.
Making the data set, yeah. And what do you think in general about the situation with data sets on the market? Do we have them or we have not enough of them? Like, what's your view on that? What's your take?
I believe that as we would need as many data sets as possible, even if they overlap in some ways. I think that the more data that is available for example, for tools like this or similar tools or even better tools, the stronger they can be. So I think that no matter how many are available already, more are always welcome.
And in this case, let's say you make this VLR data set available, then the question will be from other researchers, like how can we trust this data set? How can we know that really the lines you have there are actually the lines of vulnerability? So will you be able to somehow prove it, accompanying this data set with some tests? I don't know, somehow.
I mean, so far we have not thought about actually creating this proof. As so far we basically just trust our words when it comes to this. However, I believe that there should be some way to prove that it is in fact vulnerabilities, at least by linking the actual part where the vulnerability itself shows up, so that other researchers can see for themselves at least what we are classifying as a vulnerability, basically.
And you never met anything similar to your data set? You had to make your own? Did you try to find something similar when you started this project? Like you first were looking for a data set, but did you try to find something already on the market which you could use?
The way that this happened, the data set creation, I was not part of the data set creation project, so I don't know why it has been created or in what way. That's why Peter should have been the presenter, because he could tell you this. I unfortunately can't. However, when I joined, the dataset was already available, and since it was local and we trust our own sources, we used it. But I believe that if a dataset was available, it would have probably been used instead. But I can't sufficiently answer this question, I believe.
But I think it's important. What do you think? Is it important to have the quality of data set? It matters, right? For the entire result, yeah. So if the data set has some mistakes inside, then the total result of the project will be invalid, right?
I mean, it is possible for that to be the case. However, I believe that the model itself could technically work even if some mistakes were present in the data set, simply because since it looks for similarities, it just finds that if, for example, we presume that we have incorrectly flagged vulnerabilities, it still managed to pair apples with apples, even if those apples were incorrectly marked as apples. So I believe that the model itself would not lose too much credibility. However, the dataset, of course, would, because the dataset's quality, of course, impacts the dataset. But I believe the model could still be considered that it's an advancement, even if it turned out that the dataset was not as correct as we think it is.
Mm-hmm. And what's your next step after this project? What do you think should be what you can derive from this project and where to move next?
Well, I mean, of course, we are currently working on both improving the model in the ways that I have described earlier, and we also would like to prove its capability of finding vulnerable lines, because of course we have found these lines that we have marked as apples, but proving that they are actually apples could come from, for example, creating actual fixes for actual open source code. That's one thing that we plan on doing, to create real fixes for real vulnerabilities that are found by this model.
Mm-hmm.
I believe that both proving that the model is strong enough to find actual vulnerabilities in live systems and improving it to the point where it potentially could be used commercially are both steps we should take. Right now, we are working on a possibility of comparing it to our pre-existing solutions. However, that's still a work in progress.
And what's the language you use for this tool? Just out of curiosity.
We have used Python to create it mostly.
Uh-huh.
However, for example, the Lexer is wrote in TypeScript.
And Python probably you decided to use because the machine learning tools available mostly in Python. Am I right?
Yes, of course. There are great tools available there, and also since we have tried to make it as modular as possible, we have tried to use an easy to understand and use language, so that, for example, I failed to mention that rules can be added really easily and quickly. To do this, we believe that a language that is widely used in this field should be used in order for later researchers to be able to easily add their own 2 cents, basically.
Okay, thanks a lot. The time is over. Thank you for sending us the paper. Thanks for the presentation. I hope to see you next year at our conference.
Thank you.
Yeah.